Today we are going to talk about how to evaluate limits numerically. So to evaluate the limit numerically at a particular point, we would pick some values on the left hand side and some values on the right hand side of that particular point and find the value of the function at those points and see what's happening to the y value as x is getting closer and closer to the particular value of x at where we are trying to evaluate the limit. So here's an example. F of x is x squared. The table below shows the behavior of f of x as x approaches 3. So we are trying to evaluate limit x approaches 3 f of x, or we can say limit x approaches 3 of x squared. As x is getting really close to 3, what's happening to the y values? So we pick several values on the left hand side of 3. So we start with 2, 2.5, 2.9, 2.95, 2.99, 2.995, and 2.999. And the same way we pick the values on the right hand side of 3. Okay, and we are able to see that x is getting really close to 3 here. So this is the point where x is getting really close to 3. 2.99 is really close to 3, and 3.001 is also really close to 3. Looks like the y is getting really close to 9. So this limit is going to equal to 9. F of x approaches 9 as x approaches 3. We see that the value of f of x is equal to x squared gets closer and closer to 9 as the x approaches closer and closer to 3. Okay, so that is the limit in this case, and we can also look at graphically. We have the graph given for x squared, and we can see the y value is getting really close to 9 when x is getting really close to 3. Okay. Let's see. So we would say y approaches 9 as x approaches 3. Another way of saying is limit x approaches 3 of x squared is 9. Let's look at another example. In the last one, you might say, hey, why don't you just plug x equals 3 in there? Well, you could do that. But in the next one, we are not able to plug x equals 1 into the function because I'm going to get something undefined. So my function f of x is x minus 1 over x squared minus 1, which is same thing as x minus 1, x plus 1, x minus 1. If I go ahead and plug x equals 1 in there, let's talk about that later. Let's just look at numerical way for now. If I go ahead and plug x equals 1 in here, I would get something undefined. F of 1 is undefined. F of 1 is undefined because 1 is going to make my denominator 0 if I do direct substitution here. So what we can do here is, instead of plugging x equals 1, we can go ahead and make a table, start picking the values really close to 1 on the left hand side and really close to 1 on the right hand side. Pick the values really close to 1 on the left hand side and the right hand side, and then finally notice as you're really close to 1, so this is where you're really close to 1 and this is where you're really close to 1, see where is the y heading, what is happening to the y. The y value is approaching half, 0.499, 0.5. So we can say the limit x approaches 1, x minus 1 over x squared minus 1 is half, or 0.5. That's where the y value is getting closer and closer to. You might say how many values we need to pick. Sufficient number of values, 4 on each side are enough, 5 on each side are more than enough. Why do we need to pick several on both sides? In case your function is oscillating. Sometimes your function can be oscillating. It might look like these two numbers might be the same, but then it might be, or close by, but then it might be doing positive and negative behavior on either side. Okay, so we can see a clear trend here. We can also look at the same problem graphically. Here's a graph of that above function with the whole at 1, and we can see that y value is approaching closer and closer to, because this is where we have y equals 1, y value is getting closer and closer to half as x is getting closer and closer to 1. Okay, again looking at the graph also, we can say limit x approaches 1 of x minus 1 over x squared minus 1 is half, or 0.5. All right, one more example. Estimate limit x approaches 0 sine x over x. This is a special limit, remember that. We're going to estimate it numerically and graphically. Let's first look at numerically. So I'm going to pick some values closer and closer to 0 on the left hand side, which are 1, 1.0.1, 0.01, 0.001, and same thing on the left hand side of 0 and the right hand side of 0. Think about 0 on the number line. What values are really close to 0? So here I have 1, here I have -1. So pick the values in between. Pick the values that are getting really close to 0. Okay. Now, to estimate the limit, I'm going to look at the values that are very close to 0. Looks like 0.999, 0.999, and that seems like it's approaching 1 from both sides. 0.99999 would be almost 1. So we can say this limit, numerically, we can say the limit x approaches 0, sine x over x is 1. Remember this limit, we will be using it later in the course, so memorize, it's one of the special limits, okay? We're also going to see a proof of it later in the course. Here's graphically, we're looking at this graph. You can use Desmos to make the graph. That's what I did here. I copied this graph from Desmos, and there's a hole at x equals 0 because x is in the denominator, and that's making your function undefined when x approaches 0. Sine of 0 is also 0, so you're getting your function is undefined there. But as you're coming closer and closer to x equals 0 from left and right hand side, your y value is getting closer and closer to 1. Even though there's a hole at x equals 0, but your y value is still getting closer and closer to 1, and that would be our limit in this case. All right. Next, one more example. Investigate this limit numerically. So we want to investigate this limit numerically, x minus 9 over square root of x minus 3. Can I just go ahead and plug the 9 in there? If I do, I would get a 0 in the denominator. So function is not defined at x equals 9. I'm going to have a hole in there. At x equals 9, there's a hole. So what I'm going to do is I'm going to go ahead and pick some values. You should pick more. Pick 1 or 2 more, but I'm just going to go with these for now. So if I plug 8.9 into the calculator, so I'm going to get f of 8.9 would be 8.9 minus 9 divided by 8.9 minus square root of 8.9 minus 3, and that turns out to be 5.983. And the next one would be 5.99, 5.9983, and 9.01 would be 6.001, and then we would have 6.0001. All right, so now I wanted to estimate the limit as x approaches 9, and which numbers are really close to when x is approaching 9. These are the numbers, and it looks like the y is approaching 6. Y value is approaching 6 when x is getting really close to 9. And I would pick some more values here. In this case, I'm not picking more because I already know that this limit does exist, but you could have an oscillating function. So pick a couple more values to the left and right hand side of that C value. That's all for this video.